Welcome everybody, thank you again for coming, and thank you especially for staying as well. I know it's late, but it's just going to be even more awesome after my presentation. Okay, so before we jump into it, just a quick note on me and why I'm doing this project. I studied musicology / choreology and computer science. And after that, I worked as a music and dance researcher. I was working with motion capture data and audio data and looked at how these two interplay. So I'm generally interested in music and dance. I'm a musician myself, so when I heard about Google Magenta, it was clear that I have to do something with that. So the whole project is based on this framework by Google, this research project. It's called Google Magenta. And as they define themselves, they are an open source research project exploring the role of machine learning as a tool in the creative process. So, they say in general the creative process is about art and it's about creating things that could be music or drawings or any kind of creative process. The most part of Magenta, though, that is used now is actually within music. That's what they're focusing on right now. And with that, the other steps come. So, because I was already asked about the name of my project, it's pretty simple. I just want to be witty, and Plum is just a less saturated shape of Magenta. Interpret into that whatever you want. I just thought it's a nice name. Alright. So, in the project I was using a certain model, one of the many architectures they have in the Google Magenta project, that is called the Music VAE, Variational Auto Encoder. And what that means I'm going to tell you in a few minutes. But this is generally one of the many models in the Magenta office. They have basic RNNs and different types of approaching music creation and also like sketching and art. But the VAE, especially together with the GANs, the generative adversarial networks, is one of the most recent developments actually in deep learning. And that's what they're trying to use now to tackle like one of these big frontiers in deep learning that is part of the field of creative processes and generative learning. So before we go into the architecture, let's just have a look at data. What am I working with? I'm working with music. So I have to look for digital versions of music, of course. And there are mainly two types that you could use. These are symbolic and sub-symbolic data formats. The first one, the second one, the sub-symbolic one, is the one you have on your phones and on your computers, and you probably listen to all the time. It's the classical waveform that's here on top. That is just a description of the sound wave. That could be anything. It could be the cars passing by, me talking, or whatever. It doesn't have to be. Second part, sub-symbolic one of the examples of these is the MIDI format, where you just take into account knowledge about music and it's made for music, basically. It's not necessarily made to model sounds or general noises. So what do we use? The waveform has problems for computation. It's high dimensional, it's very long. Just take a basic sound that's at 44.1 kilohertz sample, that's 44,100 samples a second, and then take a standard pop song of 2.5 to 3 minutes, and I'll take the training set of thousands of music files. So people do it. There is the Wavenet architecture by Google. It works, but it's really expensive. So we're going to MIDI wins because it's highly organized, it's structured, it already has information about music in it itself. So that's the perfect way to take it. Now, what is a music VAE? What is a VAE? The special thing about VAEs or auto encoders just in general is the so-called latent space. That is what makes them so interesting, and that is why they are called auto encoders, because basically the output at training time should be the same as the input. You are having an input, in our case, a music file, that we put through an encoder, which is some kind of neural net, and that reduces the dimensions of our input. In the case of the music VAE, it's 512 dimensions. And this is the latent space we are working on. This Z in the middle, this is the latent space. And when training it, you put the decoder, into the decoder you put that samples from the latent space. And what you get out should be ideally what you're getting. This is a little bit weird. For a standard approach, usually you want to get something else out of a neural net. But in this case, the good thing about it is that we can create this latent space according to our data set. And we build a space that represents our data set in a much lower dimensions, which is wonderful because we can work on that latent space later. So for the curious ones, how is the actual music VAE built up? It's comparatively simple, actually. So the encoder just takes in the MIDI file, it transforms it into a machine readable format, of course. Instead of the channels that you have, you basically have just matrices saying there's a note, there's not a note. And they have two layers that encode the MIDI file. The first one is basically just embedding it into a different representation, as we already saw with the NLP approach earlier, for example. And the second layer is then taking these embeddings and encoding it into the latent space. A little optimization that people do with autoencoders usually is that they don't just put it anywhere in the latent space, but they try to force it within a standard norm distribution. So the latent space actually better depicts the original space. So neighbors that are close in the original space are also close in the latent space. That's the idea, and that's why it's called Variational Auto Encoders. And the decoder, they published a paper like a few years ago where they did this hierarchical approach where they introduced an addition layer. It's again basically just two layers that do the main work, the heavy load. And the first one is the conductor layer, which makes an embedding out of the latent space for each measure that you want to generate. Because what they found out is if you just take LSTM, unidirectional LSTM, you get a lot of information is lost from the latent space actually. So they just split it up again for each measure, make an embedding, and from that you can feed it into an LSTM and get out whatever it is that you want to get out. Melody, drum line, or whatever. Now, how do they use it? I use it a lot actually. I took a data set that's called the LaskoskiÄ data set that has about 170,000 files in its original form. I took a subset of that only that has additional metadata, such metadata such as the artist's name, the track name, the album release, the year, and especially the genre. And what you can see here is just the general distribution of what they were labeled as in the data set. The data set is connected to the Million Song data set, that's a different one. So this is human labeled data. And you can see that with labels such as American and British, and classic pop and rock, and somewhere there is pop as well. And you have hip hop, R&B, and dance all in one table. The good thing is these are still labels and these are still genres and they are valid. If you listen to some of the music, they are valid. So what I did was I was trying to analyze music because in the first place I was a musicologist, so I was trying to analyze it first. And I did that, and I just took, for an example that I want to show you, just two genres, and coded these into the latent space, and toned it down with a TSME to get less dimensions again, to better visualize it, because we have 505 dimensions, right? And I just embedded it into 2 dimensions and to show you that it kind of works. I mean, that kind of looks like a textbook sample for a clustering approach, right? And I look at it, and for visualization purpose, I run an SVM with a linear kernel over it, and yeah, it does. There are outliers as any example, but if you listen to these songs, yes, they are country songs, yes, they are hip-hop and R&B songs. And now, the interesting part, that I play around with a lot, and I wish I could show you so many audio examples, but unfortunately we don't have the time. What you can do is, for example, work in a latent space. So let's say I get the mean of this cluster and say that's my average hip-hop, R&B, and metal song, and dance song. I can do the same thing for the country song, for example, and say, hey, this is my average country song. If you decode that, if you decode the general country song, it sounds a little bit good because it feels like all department delivery sites are trying to have a rap battle or something, because of course it's somewhere in the middle, but it represents a general average intermediate space. And so what we can do is basically look at this vector here. Yes, you can see. Like move one genre into the other genre. You can just freely move around in the waiting space. And I could, for example, just make this song. Oops. That should be straight over. More sound like this song. So I did a lot of this, and I listened to a lot of these examples. It was wonderful to hear like just some nuances in drumming, for example, when we go from one country song to another, or from I don't know, heavy metal back to the 1960s ballads or something. That's really interesting. And yes, I know everybody wants to have an audio example. I want to, so I'm doing it. This is me. People told me not to say it, but it's me. So it's still me. It's not a waveform. So we have two examples here, two really short examples, which show the limitations of the smallest model, because they can't take just one big file and processes. You have to make it small, make it one instrument at a time, one measure at a time. And I try to split up a little bit, take one measure, and put it in. So this is the original sample A. Feel free to dance, yes. You might know it. This is the second example, example B. So maybe some of you know it, for those who don't. Okay, so the first one was ABBA, basically from 1976. The second one was Dancing in the Moonlight from Ashley King Harvest, some of you may know from the top loader version of 2003 movie. Which makes a difference because this one is actually much more bluesy, jazzy, that you can hear the bass line. And what I did now is just an example. We go slowly from one version, ABBA, over to the King Harvest version. So I put it in, I encoded both examples, and by interpolation, I wandered over the safety space into the other song. This is wonderful to hear, especially with bass line and drums. And companies is like video checks. That's all your tech, yeah. You can imagine. Yes. I'm really sorry about that. One last try. I say yes, to do everything. And since that doesn't work, I just want to show you like that. the middle, it was going a little bit crazy. But that's all. I mean, this was 6 steps through a big latency. So I was going basically to put it down to different jumps, for example. So you just have, that's a little bit manual fine-tuning that you have to try. You can do the first 2 steps, so basically really close, but the one in the middle will go a little bit crazy. But in general, that is perfectly fine, and that gives us so much opportunity to support. And to end it, just limitations and perspectives, a few words on that. As I already said, it's a limited amount of training models that we have currently in Magenta. They have about 10 models, and they only work on restricted data. So we have, for example, 1 to 2 measures, you have 1 to 3 instruments or whatever. But the good thing is, you can train it. If you have a big enough data set, if you have the computational power to do it, it's super easy, and you can make your own music. You can make your own covers easily with that if you're not a musician that usually does it themselves. So it is possible, and Magenta is still in development. They're not super far yet, but they already did so much. And what I'm going to do next is use the latent space actually and work on the audio trait latent space, because they have like over 100,000 examples in that, and you can generate music just from the latent space itself with generative models themselves again. And for those who wonder, this is not just applicable to music. This is an approach in creative, like machine learning and generative models that you can adapt it to any kind of data. Could be customer data, tabular data. You can cluster things with that. You can find structures in the latent space, and you can, for example, generate new synthetic data by just creating a latent space and sampling from points that you didn't have. So this is basically just the imagination that moves through the applications of these kinds of things. And that was it for me.